Welcome to the presentation of RGB-D Inertial Odometry for Resource-Restricted Robot in Dynamic Environments. Most of the visual inertial odometry algorithms are based on a steady world assumption. However, various dynamic objects exist in the real world, and more mobile devices are equipped with depth sensors. Existing real-world algorithms still struggle to output robust instant state estimation in highly dynamic environments on embedded computing platforms. At the same time, increasingly embedded computing platforms are equipped with AI computing units, such as Huawei Atlas 200, NVIDIA Jetson, etc. It enables live deep learning networks to run on the embedded computing platform in real time. This study proposed a real-time RGB-D inertial odometry system for resource-restricted robot in dynamic environments named dynamic rings. Three-main threads run parallel in dynamic rings. There are object detection, feature checking, and state optimization. Color images are passed to both the object detection thread and the feature checking thread. IMU measurements between two consecutive frames are pre-integrated for feature checking, moving consistent checks, and state optimization. For each incoming image, the IMU measurement between frames are used to predict the motion of features. The KLT sparse optical flow method looks for a matched feature in the current frame. The successfully checked features are turned red, while those that fail to be checked are marked as unstable features. In order to avoid the repetitions and aggregations of feature detections, a circular mask centered on the stable feature is set. The region where the unstable features are located is considered an unstable feature detection region. According to the mask, new features are detected from unmasked areas in the current frame. The above means can obtain uniformly distributed features to capture stable constraints and reduce the amount of features. Long-term feature checking can reduce the time consumption with the help of grid-based feature detection. Unlike traversing the whole image to detect features, only the grid with insufficient matched features will conduct feature detection. The grid cell fails to detect features due to the rich texture or is covered by the mask will be skipped in the next detection frame. The thread-proof technique is used to exploit the parallel performance of grid-based feature detection. Most feature points can be stable checked through the above improvement. However, long-term checking features on dynamic objects always come with abnormal motions and introduce one constraint. A real-time object detection method, RealO, is used to detect dynamic objects. If detecting bounding boxes cover a large region, blindly discarding features in bounding boxes might result in no features. Therefore, semantic segmentation like masks are helpful to check features not occluded by dynamic objects. As the farther the depth camera measures, the worse the accuracy is. This problem makes some methods such as filling k-means, which make full use of the depth information, exhibit proof performance with a low accuracy depth camera. Considering that the bounding box corners of most dynamic objects correspond to the background points, and the dynamic objects commonly have a relatively large depth gap with the background, a set of points in detected bounding boxes and depth information are integrated to define semantic masks. When the dynamic objects have a close connection to the background or is behind an object, the depth threshold is defined at a distance from the dynamic objects. The semantic mask is set a weighted depth threshold. Each incoming feature's depth is compared with the depth threshold on the semantic mask. If the feature's depth is smaller than the threshold, consider as a dynamic one. Otherwise, the feature is considered as a stable one. Since object detection might sometimes fail, we assume that the dynamic objects in adjacent frames have a consistent motion, and predict the following detection results to compensate for misdetection. Also, a geometry-based moving consistent check is used to handle unknown dynamic objects and bleeding points on the edge of objects. In open knowledge dataset experience, the proposed dynamic rings outperform other state-of-the-art algorithms and can effectively deal with complex dynamic environments and improve robustness and accuracy. In real-world experience, we set up a micro-area vehicles, the Intel NUC charged for peripheral management and other core functions requiring more CPU resources such as planning and mapping. The edge computing device Atlas 200 as auxiliary equipment over instant state feedback and object detection to the onboard computer. An aggressive flying experience showed the robustness and efficiency of our proposed algorithms. The controllers are under position mode and tie the state estimation results from dynamic winds. The pilot controls it with deliberate aggressive motion. Large-scale outdoor datasets with moving people and vehicles on the Tsinghua Shenzhen campus are recorded by the handheld aerial robot above for safety. In outdoor environments, the depth camera is limited in range and affected by the sunlight. The dynamic feature recognition module can still summon dynamic objects but with a larger sparse regions and outperform WIN's RGB-D. This part compares WIN's mono-mix RGB-D and dynamic WINs for runtime analysis. With the same parameters, dynamic WINs show significant improvement in efficiency in both embedded platforms, and is the one able to achieve instant feature checking and detection in Huawei RTX200 DK. In the recent world, with the help of dynamic WINs, we achieved a fully onboard aerial manipulator robot catching cast on Huawei RTX200 DK with 8-core A55 ARM CPU and a 2-core Huawei DaVinci NPU. Thank you for your listening.